Okay, so today I'm going to start talking about Laplace transforms, which is 10.1. So Laplace transforms are a powerful tool to solve differential equations that, if you really learn them, you may find yourself wondering, why did we bother with these previous ways we had of solving differential equations? They can't do everything. I don't want to make it sound like everything we did so far is like useless, but these provide us with another way to do some things that we were able to do before, but you might prefer the new way for some of these things. But let's not get ahead of ourselves. This takes some build-up. Maybe by the end of today I'll solve a differential equation using this stuff, but we have to, first I have to tell you what it is. So the Laplace transform, it's something that you do to a function and it gives you another function. So say I have a function f. The Laplace transform of lowercase f is going to be capital F, which is some other function. And I'll tell you what it is. So little f is some function. So big F is going to be this function. And something to keep in mind about this is typically we consider little f to be a function of t. We use the letter t for that variable. And big F is a function of s. And the way you evaluate big F of s is you put that s here, and you do this integral from 0 to infinity of e to the negative st times f of t dt. And that depends on s. T is like a dummy variable for this integral, so there's no t's in the answer. When you put in the limits of 0 and infinity, the t's all go away, or they're replaced with 0, or they're replaced with the limit as t goes to infinity. So there's no t's in this once you evaluate it, but there are s's, and so that's the function of s that it is. Okay, so in the book, there's a table of Laplace transforms of like if little f is this, then its Laplace transform is big F, which is this. I'm just going to check a few of these. I'm not going to check all of them. I encourage you to just refer to the table from now on after we check a few of these. And yeah, so before I do that, before I check any, let me just say, Laplace transforms are a lot like, and this is a slightly dangerous comparison to make, but they are a lot like derivatives and integrals, just in the sense that these are all things that if I give you a function, you give me another function, and it could be the Laplace transform of what I gave you, it could be the derivative of what I gave you, it could be the antiderivative of what I gave you. The analogy that I'm making is just that these are all things that take functions and give you other functions. And if you just learn the rules, like we all learned our derivative rules, we all learned the product rule, the quotient rule, and these basic derivative rules. These are like your basic Laplace transform rules in that way. So these are the basic rules that we're going to use to build up, and then we'll basically be able to do the Laplace transform of any reasonable function that life would throw at us. Anyway, let's check some of these. I'm going to check the easiest one first. If little f is just the constant function 1, then its Laplace transform is 1 over s. So this will be easy enough to check. I'm just plugging in 1 here. So I get this. This is, of course, oh geez, what are these called? Improper integral, because we have infinity in the limit. So what do you do with these? First, I would find the antiderivative. The antiderivative of this with respect to t would be this, right? Because if I did the derivative of this with respect to t, the negative s's would cancel, and I would get this. So this is the antiderivative. Normally, of course, with an indefinite integral, or sorry, a definite integral, I would put this number here and this number here. Of course, I would like to avoid writing infinity here. So what do? If you remember, for improper integrals, instead of doing infinity, I do the limit as b goes to infinity, and then I write b in the place where I was tempted to write the symbol for infinity. That's how we handle this. Okay, and keep in mind, and maybe I should emphasize this, this is an integral with respect to t. So these values go in for t now. T goes to 0, t goes from 0 to b. So limit as b goes to infinity, I put in b for t. And when I put in 0, well, e to the 0 is just 1, so I just get 1. Right, and as b goes to infinity, I want to say that this goes to 0, but now do we get to assume that s is always positive? I believe we do in the definition. Yeah, or actually, yeah, okay. So in the book just says, for all values s for which the improper integral converges. This is going to converge as long as s is positive, and that's, I guess, if I'm careful. If I'm careful, that is actually what the table says. It's that this is true for s positive. So maybe I should emphasize we're doing s positive. But as long as s is positive, this is like e to the negative infinity, which is like 0. So as b goes to infinity, this part goes to 0, and I'm just left with this part, which is 1 over s, and that's what we're supposed to get. Yeah, so we're happy. Let me check a slightly less easy one. I'll just check the second one, the Laplace transform of t. Of course, we're going to check that this is true. I just wanted to write it down so I didn't forget it. So, just moving you a little bit here. All right, let's check it. Well, it would be the integral from 0 to infinity of, now I'm using this formula, but I'm putting t here and not just 1. So this would be t e to the negative st. Right? dt. And this turns into just a little bit of an integral problem. Maybe I will cordon off some space here just to find the antiderivative of this thing. This looks like the type of thing where we would use integration by parts. U should be t, dv would be e to the negative st dt. du is just dt. And v, the antiderivative of this is, we did this before, negative 1 over s e to the negative st. Right? Trying to be space efficient here. So this is equal to u times v minus the integral of v du so I get my first term and then I guess what can I do here? Keep in mind that the integrals are with respect to t, so as far as we're concerned, s is a constant, so this can come out. So we would have a plus 1 over s times the antiderivative of e to the negative st, which would again be negative 1 over s e to the negative st. So what do I get? I get negative 1 over s t e to the negative st minus 1 over s squared e to the negative st. And, right, I guess maybe I should put plus c on this integral, but I'm about to plug it in with limits, so the plus c wouldn't really matter. Right? So where am I now? I was doing this, and I didn't know what the antiderivative was, but now I do. So because this is an improper integral, I'm going to basically replace the symbol for infinity with the letter b, and I'm just going to do the limit as b goes to infinity. But other than that, what would I do? I know the antiderivative now. Let me actually write this a little bit better. I'll write t over s. E to the negative st minus 1 over s squared e to the negative st. And I'm putting in 0 and b. Right? So let me just take a step to put that in. The limit as b goes to infinity of, so once again, b goes in for t. I didn't emphasize it the way I did last time, but b goes in, like these numbers, they go in for t. So it's like that. That, and then I'm using parentheses so that way I won't forget to distribute this negative sign when I write what I'm about to write. I'm putting in 0 for t, so okay, so that's good, so this whole thing is 0, but this thing is negative 1 over s squared. Well, e to the 0 is 1, so it's just that. Okay. And let me, I realize this one is just a little bit harder than I realized, but it's not a problem, we can do it. The answer that we're supposed to get is 1 over s squared, and I basically see it here. The rest of the work is going to be showing that this stuff goes to 0 as b goes to infinity. I can even see part of that here. It's clear that this part goes to 0. Because once again, s is a positive number, b is going to infinity, so this is like e to the negative infinity, which is 0. And this is just a constant, so because b is going to infinity. S is not going to infinity. S is just a positive number. So 1 over s squared is just a constant. This is like 0. So this term is going to 0. It is not as obvious that this term is going to 0. For this term, this is a, there's a name for these, indeterminate form. This is like infinity times 0, because this part is going to 0, because of, we said that before, that this part is going to 0. It's like e to the negative infinity. But b is going to infinity, so in other words, this is like infinity times 0. So we have a slight issue here. We're not in big trouble. We are going to be able to show that this goes to 0. I'm just pointing out that there's a little bit of work to show. So maybe in terms of being the most organized way of handling this, obviously I don't have enough room on this sheet of paper. I am just going to state what the answer is going to end up being, and then on the next sheet of paper I'm going to justify the claim that this goes to 0. So I'm telling you what the final answer we're going to get is, but I'm acknowledging that it is not entirely justified yet, because now all I have to do, all that's left, is showing that this goes to 0. Negative b over s e to the negative sb. Yeah, so this isn't a big deal if you remember what to do. We just use L'Hopital's rule. For infinity times 0, what I would like to do is use L'Hopital's rule, which is good for two types of things. L'Hopital's rule is good for 0 over 0 or infinity over infinity. So what I do is, if I have multiplication like 0 times infinity, I just turn it into a fraction, like I put this thing on the bottom, or I do something like that. Probably the best thing to do here is for me to just, oops, don't forget about this s, but I just put this on the denominator. Now this is infinity over infinity. B is going to infinity, so the top's going to infinity. Also, the bottom is going to infinity because s is a positive number, so now on the bottom this is like e to the positive infinity. Now that I have something where L'Hopital's rule applies, I can do, well, I can do L'Hopital's rule. I do the derivative of the top, and when I say derivative, b is the variable here. So it's derivative with respect to b. So the derivative of b with respect to b is 1. The derivative of this with respect to b is, well, let's see. S is a constant, so the s just stays. The derivative of e to the sb would be e to the sb times s, because I'm doing the chain rule, and the derivative of sb with respect to b would be s. Right? And now I just look at what I have. On the top is no longer going to infinity. The top is just 1. However, the bottom is going to infinity still. So I've got 1 over infinity. This limit is 0, just like we said it was going to be. So we do get this answer after all, because we found that this part went to 0 just now. We already knew that that part went to 0. That was easier to see. So all that's left over is this. And that's what we got. Okay, so let me upload this, and I am going to do at least one more example where we find a Laplace transform.